Hello and welcome back to the USAFA Chemistry Lab. Today we're doing characterization of an oxalate compound lab. Okay. So the oxalate compound that you will be characterizing is this one right at the top. It contains iron, contains potassium, contains the oxalate anion, and it contains water molecules that are also bound to the compound. Okay. So there are 4 different subscripts down here, L, M, N, and X. So L will be determined for you via different means, and that's given in your procedure. X will also be determined by a different means. Today, the only thing we're going to be determining in the lab is the N, is the mole percent of the oxalate anion within this compound. The M for the potassium will be determined by what's left over. Okay, so we'll be determining the mole percent of the oxalate anion in this compound via a titration. Okay? So this is the formula or the chemical equation for the titration. The oxalate is reacting with permanganate in acid to produce carbon dioxide, so you may see some bubbling in the reaction, manganese 2+, and water. Manganese 2+ is colorless, but the permanganate ion is purple, and the oxalate ion is yellowish green. So it's an easy lab to see the change in the concentrations based on the color changes. Okay, so what happens during a titration is that at the start, in this case, we have oxalate alone in solution. The moles are X. We don't know that. That's what we're trying to determine. And the moles of permanganate is also 0 before we've started. And then some time has gone by. We're halfway through the titration. We're adding permanganate from the burette, and then halfway through, the number of moles of oxalate has gone down by half, but the moles of permanganate is still 0, right? Because it has all reacted with the oxalate that's in solution. It's not until the very end, at the end point, where there is any permanganate existing in solution because all of the oxalate has reacted. So the moles of oxalate would be 0, and the moles of permanganate is just barely greater than 0 at the end point. It's actually supposed to be the point where the two are equivalent, but you can see the difference because just a tiny, tiny bit, 1 drop of permanganate past the number of moles that it takes to react with all the oxalate gives you just a light pink color. Okay, so that's what we're going to be doing in lab today, and that's good. Okay, so so we have our burette. Our burette is partially charged at this point with permanganate, potassium permanganate. So we're going to add some more. So again, when you're charging a burette, you definitely want to make sure the stopcock is closed, and you don't pour any liquids above eye level. So we'll add some more permanganate here. And that'll be good. And you want to note that volume, okay? Doesn't matter what the volume is as long as you know what it is exactly, okay? So note that. For us, it's about, and you can actually use this card to check what that volume is. You can see the contrast between the white and the black helps you find the bottom of that meniscus a little bit better. So for us, that's about 11.83. Okay, so we'll put it back on here. And it's also very important for this experiment to note the concentration of the potassium permanganate that's written on the bottle. So in this case, it's 0.01 molar, but it might be slightly different in the one that you use when you're in the lab. Set that aside. Okay, now this is the oxalate ion, or the oxalate compound. It has an oxalate ion inside it. So we want to measure out approximately 0.1 grams. And here we have approximately 0.1 grams in a little weighing boat. So we're going to put this in the beaker. Okay. And we're going to add to that approximately 15 milliliters of sulfuric acid. And to that, we're going to add a stir bar. And we're going to go ahead and turn our stir plate on. And we're going to turn our heat on. But this is important. Go ahead and turn the heat pretty far up. But as soon as you see condensation forming, some of that is evaporating. As soon as you see that, you need to turn the heat all the way off, or else you'll get some side reactions that will lead to lead to an inefficient reaction here. But the reason that it needs to be hot is because when the permanganate drops in and mixes, that color change will be very slow if the solution is cold. So you need the solution to be hot in order to see that color change quickly so you can get an accurate endpoint. So we'll wait just a minute or so till we start to see condensation. See some condensation starting to form on the sides of the beaker. That's probably good. So we'll just turn the heat all the way off. Obviously keep the stirring going, and now we can start to add our potassium permanganate. So when you add some, you'll notice it turns the solution a little bit brownish as the two colors mix, but then it goes away. Add some more, brownish, goes away. Some more, goes away. So titration is a technique that requires a lot of patience because you don't know exactly how much you need in order to get to that endpoint. Okay, so here we are getting close to the endpoint. You can tell because the solution has gotten a lot more paler in yellow-green color. So I'm just going to start to go real slow. And eventually I'll just go dropwise because I don't want to pass that endpoint. Again, that endpoint is the solution will go from the color that it is now, greenish yellow, to clear, and then just a hint of pink, and then that's the endpoint. Again, exercise that requires a lot of patience. I think we're almost there. So close. But it's not until that pink color persists that you're actually at the endpoint. And technically, I'd say you're there. That's it. Okay. So just a very faint pink color. We're at the endpoint. So now you measure this volume again, and you take the difference. So you know the volume of the potassium permanganate that you added to get to the endpoint. So you'll do this titration twice, and then you'll calculate from there. Okay, so to do the calculation, you know the volume of potassium permanganate that was added. You can convert that to the moles of potassium permanganate because you know the concentration of the solution. From there, you can calculate the moles of oxalate anion that were originally in the solution. And then from there, you can from the molecular weight, you can calculate the mass of the oxalate anion. And knowing that the original mass of the whole compound, you can calculate the percent mass. And then by taking the mole percent of oxalate and the already known mole percent of iron and the already known mole percent of water, you can use that information to calculate the mole percent of potassium and round that all out to integer numbers, and there you have your empirical formula. And that is the end of the lab.